seminar, we're gonna um, walk through an interesting blog post on attention models that I came across quite recently. And here you get the link, so it's provided by Eurotech, and it's very interesting blog post, very nice blog post on a very interesting topic. Okay, so the idea behind attention mechanisms in neural nets derives from neural processes that have been studied in neuroscience or computational neuroscience, in particular within the context of visual attention. And that is that we typically focus on specific areas of our visual inputs in order to compute responses. And that, as you can imagine, it does have quite an impact on the neural computation of visual information, as we do need to make a selection on the most relevant information, in contrast to using all available information, and resulting in a large part of the available information not being relevant in order to compute a relevant response. And now this particular idea has been applied to deep learning in various areas. So it's and it actually achieves quite good performances. So let's have a closer look at that. Okay, to follow an example that is given here for image captioning. So what is that? We start with an image at the bottom, and we feed this into a neural net, or actually a combination of neural nets, and as an output we want to get a description of what is present within the image. And so how can we go about this? We can start using a trained convolutional neural net on the image that would produce some hidden state H. And this hidden state would subsequently be decoded based on the application of a recurrent neural net, which then would generate each word of the caption. So, and this is actually the example given here. We got this hidden state. In this case, there's LSTM networks that subsequently produce the the output sequence. So the general issue with such an approach is that whenever the model tries to generate the next word within the caption, that word only describes a part of this image. And therefore, to use the entire representation of the image given by this hidden state H in order to condition this generation of each individual word suffers from not being able to produce different words within different parts of an image. And that's actually where the attention mechanism becomes very comes in very handy, because using this approach, we can first divide an image into individual parts, and then compute representations using CNNs, convolutional neural nets, for each of those individual parts. And therefore, whenever the RNN, the recurrent neural net, is generating a new word, this attention approach does actually focus on the specific corresponding part of an image, and therefore the decoder mechanism that is used only utilizes the specific parts within an image. Okay, so let's have a look. I'm sorry, let's have a look at an example that is also presented by the authors of the blog post and actually refers back to this paper by Winyas, Real et al. So what we can see here is that on the upper row of this figure, what we see is for each word of the given summarizing caption of this image. So we can see for each word of the caption what part within the image, and that is defined in white, was used in order to generate the output. Okay, so we can have another example from the same paper. Yeah, again, looking at the relevant parts, and as you can see, a woman is throwing a frisbee in the park, for example, and the particular area is highlighted. The same goes for the other examples. Okay, so let's go into an explanation on how the attention models do actually work. And so we start with this depiction here, kind of like having this attention model as being the black box, and we're going to go into this in each step. So in general, the attention model represents a function or a method that does take input arguments. Here labeled as yi to all the way up to yn. And so if we compare this in our preceding example here, this would be the h0 to hk. So there's we're going to get back to this example of image capturing later, or just to get the connection here. So in our black box here, we're working with yi to yn, as well as some context c. And the output vector set is then seen as the summary of the y's. And again, the idea is that we focus on the information that is also linked to the context C. And we're going to see this in more mathematical terms as well later. Okay, so in our previous example, the context was the beginning of the generated sentence, and the yi were the representations of the parts of our image. And finally, the output was a representation of the filtered image, whereas we, using this approach, we had the filter to put the focus on of the interesting part for the word that was currently generated. Okay, and so given the mathematical framework, I'm going to briefly mention that already here, because this is the one interesting feature of the attention mechanism, is that in a formal setting, we would say that we would return, as output set, we would return a weighted arithmetic mean of the individual y's, yi, y1 to yn, and that each weight per y is chosen according to the relevance of each yi within the context C, and that actually leads to being able to plot these weights, and that actually, as we've seen in the figure before, this enables us to actually draw the areas that the neural network sort of focuses upon, so we can actually see what's going on. And that's also something very interesting in the context of understanding what's going on inside neural nets. Okay, so let's go one step further and open the black box. So again, you see your inputs on the context C as well as our yi up to yn, and our output set. Okay, so first let's put the focus on our context C, and as well as yi that are defined, as we mentioned, as parts of the overall data. And let's briefly use this and go one step up into the attention model. So in the next step, excuse me, in the next step, what the net does is to compute some in-between output values per each y and c using the 10H function. And formally, this is defined within the equation below the depiction here. So mi is the 10H function of the weights of the context times the context plus the weights of y times yi. So the idea being, what we do here is to compute an aggregation of the values of yi and c. An interesting aspect is computationally also very effectively computable, because we can compute each mi without independently from all we can compute each mi for each yi without independently from all other y's. So after this, we basically proceed within the model and do compute the weights using a softmax function. So basically, what is interesting is that the softmax function is behaving like an argmax function, but it is differentiable. So, and we can make use of this. So say that we would have an argmax function where we, for overall inputs, where we would only have one in the output in order to tell us which inputs provides the maximum of the function. And then we can define the softmax function in a way or it is actually defined as the individual value over the sum of all values. So it's not as, it's a softmax. It provides an output to show us which input is bigger, but it's not just a binary switch in order only the argmax is provided, all others are set to 0. With the softmax function, we can actually even interpret this as probabilities to identify, of course, what is the highest value. So the highest value will have the maximum value between 0 and 1, but all the other ones will also be shown. And basically, when using the softmax function, it adds up to 1. Okay, so, and again, if you will, we could see the argmax function as kind of like the extreme case of the softmax, and that is when the probability for one of the inputs is maximum, is 1. Then basically this leads to all the other inputs have to be 0. Also in the case of a softmax. Okay, so getting back to our example here, we compute based on the softmax function, we compute outputs for each individual, integrating the mi to m1 to mn. And okay, how can we do this? This is actually the example for the softmax computation given here. So here, what we have is that Si is proportional to the exponent of the weights for m and mi. And yeah, as I mentioned, the softmax sums up to 1. So the sum of all results here Si needs to be 1. Okay, and this is actually, again, this can be seen as the output here given the context and a computation per individual input y. What we see is the relevance of a particular input y according to the context. And as an output, we build, based on these individual softmax computations, we build an arithmetic mean, as you see below. So this is actually the softmax represents some sort of weight multiplied by the original input, summed over, and that is our output C. Yeah, set, sorry. Okay, let's look at a small modification of this model. So first we can replace the 10h function by something else. And the only thing to keep in mind, or the only crucial fundamental aspect, is that the function that we chose does mix together, mix up C and yi. Yeah, for example, some version could be to compute a dot product between C and y. And that might be actually a version that's easy to understand. Okay, so, and now let's look at two variations for attention. And actually, we've looked at already one of these versions of attention. That was the what was called soft attention. And that is the mechanism that we've already looked at. And it's called soft attention, given that it is differentiable. And therefore, it's a differentiable deterministic mechanism, which we can use to plug into an existing system, given that it's differentiable, and resulting in the gradients being propagated through this attention mechanism, a black box, while they're also being propagated at the same time through the rest of the entire network. And now hard attention, on the other hand, just like the argmax, if you will, does represent a more stochastic procedure. And here, in contrast to using all hidden states as the input for the decoder, the system rather does a sampling procedure and samples individual hidden states yi with the probability given by S. So in order to then propagate a gradient through this process, it is estimated using Monte Carlo sampling. And this is actually what we see here. So what we have here is this layer. Instead of, as you can see, this way, we have a random choosing of individual hidden state outputs. So now with this, let's go back to our image captioning example in order to understand this in the context of applying attention models. So now we included this attention layer, if you will. And now we can have a look at what is going on in case that we want to predict a new word of the caption. So what happens is that if we have already predicted up to the ith word, then the hidden state of the LSTM model here would be HI. Okay, so that makes sense. So therefore, now we select the relevant part. We focus on a specific part of the image using HI as our context, right? So for example, H1 is going to be our context for our attention model. And then the output of our attention model, that is set, is the representation of the image and filtered in a way so that we retain only the relevant part of an image and use this again as an input for the next LSTM model. And this in turn returns the next hidden state. Okay, and so now we can basically use this approach in the context of machine translation. And there's some work by Bardanao et al. That actually proposed a neural translation model that learned to translate sentences from one language into another language using an attention model. So let's have a look at actually a translation model without attention. And the way this is done is using an encoder and decoder model. So the in this case, the encoder model is using or it uses as input sentences in English. So the idea is to translate from English to French. And it is basically a recurrent neural net and produces this hidden state H. And this hidden state then conditions the decoder recurrent net in order to produce the outputs in French. So now we, for the translation idea, we use the same intuition that we've been looking at image captioning. And now here, when we want to generate a new word, we typically do translate a single word from the original language into the new one. However, using attention, again, we can, for each word that we want to translate, focus on only the relevant part of the original text. And therefore, what we do is here we make a slight modification, or the slight difference to the image caption model is that now that the hidden state HI is the hidden layers of the recurrent net. So let's have a look at this. Okay, so here's this example. And what we see here is that instead of producing just individual hidden states, a single hidden state, that corresponds to the whole sentence, now the encoder does produce multiple hidden states HI that do correspond to that word. And therefore, each time that the decoder produces a word in the new language, it does determine the contribution of each of the hidden states of the encoder as its input. And typically this is only a single one, but yeah. So the contribution that is calculated again using a softmax function. And this way we can compute the attention weights. Okay, so what we can also do is that we can see this process as an alignment, because that the net typically focuses on a single input word each time when it produces an output word. So that also means that most of the attention weights are black. And this particular example, again here taken from the work of Badano et al. What we see is that most of the attention weights are for an individual input word are black, while only individual ones are activated. But as you can also see, this is the advantage of using the softmax over this argmax approach, is that it allows for multiple words. So let's take this example here, signed, and then we have our putative corresponding words in French. And as you can see, the most influential word is signed, signé, and this is actually chosen. And we get this 4 other words, and you can see most of those are actually black, but again, there might be cases where we allow for multiple words to have an influence. And yeah, so what we again see in this plot is the attention weights within the translation process. And yeah, it also allows us again what in this case of neural translation, what the RNA actually has learned, and that gives us an insight into the neural net. And that again is very interesting, given that usually this in the context to learn what's going on in a neural net is difficult to decode. Okay, so this is it on this very interesting blog post. Let's give you the address one more time. Yeah, you might. There's some further reading there, so it's really nice. And yeah, I hope you like it.